Alright, so picking up where we left off in the last video with scalars, vectors, distance, and displacement, we're going to talk about a new scalar and a new vector, and those are going to be average speed and average velocity. So we'll go down here. So average speed is something we're kind of familiar with in day-to-day life outside of a physical sense. We use this to calculate road trips. If I went 500 miles and it took me 10 hours and how fast was I going and so on and so forth. And then the vector quantity, the vector parallel to that, is average velocity. So we have average velocity and average speed. So we're just going to work through another example and define these terms before that so we can get an idea of what these mean. So in physics, when we have an average quantity, what we usually denote that by is a bar. So I've got S here for speed and a bar, so just average speed. And that's going to be our scalar distance that we defined in the last video divided by the change in time. And remember that delta there just means change in. Our average velocity, on the other hand, is going to be V bar, and that's going to be our displacement vector divided by the change in time. And just to get a clearer picture, this is x2 minus x1 divided by t2 minus t1. A lot of times this delta t will just be written as t because a lot of times our initial time is just 0 seconds, but more formally it's t2 minus t1. All right, so let's look at an example. So let's say I start walking left and I go some distance here in this direction, and then I get down to the end and I come almost all the way back, and then I go from there a little past halfway. So let's see, we'll call this 10 meters, we'll call this other piece 8 meters long, and we'll call the final piece maybe 5 meters. All right, and let's say that that took me a total, all of this, my time for all of this was, we'll say 15 seconds. So 15 seconds for all of that. What was my average speed? Well, S bar, so I need my distance divided by my change in time. So my distance, well, I walked 10 meters, and then I walked 8 meters, and then I walked 5 meters. So this distance is just going to be 10 plus 8 plus 5, and divided by my change in time, we said was 15 seconds. All right, so 10 plus 8 gives me 18, plus 5 gives me 23. So this is 23 over 5, and our units were meters per second. And we can get a decimal out of this. You can just type it into your calculator. 23 over 15, that's about 1.53 roughly, about 1.53 meters per second. So now let's look at the same example and calculate our average velocity. So the exact same example, but we want the average velocity now. Well, my velocity, my average velocity, is going to be my displacement. And notice we have to take into consideration direction here. So this movement, remember in the last video we defined right hand motion to be positive and left hand motion to be negative. So here I have left hand motion of 10, right hand motion of 8, and back left of 5. So my average velocity is going to be negative 10 plus 8 minus 5 divided by, and our time is again 15 seconds. Time is an example of a scalar quantity. Our displacement is a vector and our velocity here is a vector, but time itself is just a scalar, so it's just 15 seconds. So what does this give us? Negative 10 plus 8 gives us negative 2. Negative 2 minus 5 gives us negative 7, and then divided by 15. Now, so negative 7 over 15 meters per second, and that is roughly That is roughly 0.47 meters a second, and we can't forget our negative sign. So this is taking into account direction, and notice it's very different. Yes, our speed was 1.53 meters a second, but that was magnitude only. Over this entire time interval, we moved this fast, but in the negative direction. That was our average there. Now, in physics, what we have a lot of time, we won't just have examples like this where it's written out in left to right lines. What we have often is position versus time graphs. Position versus time graphs. So let's go down here and see what that looks like. So I'll move this down here just for comparison's sake. Now, what would the position versus time graph look like for this? Well, I'm going to draw some axes. An axis here and here. And so normally in math, we're used to seeing the x labeled up here, or down here, excuse me, and the y right here. But here, that's not the relationship we're interested in. What we're interested in is the horizontal position versus time. So I'm going to put time down here, and I'm going to put position in the vertical. So if we're saying that we started here, we can call that 10 meters. So we'll call this position right here 0, and we'll call this 10. And then the second piece, I went from 0, we can call that 8. And then I went from 8 minus 5, and we can call this one 3. So let's graph this on our position versus time graph. So at time equal to 0, time equal to 0, I started at 10. So if I have labeled here, we'll say this is 10, and that's where I started. So we'll make the red mark there. And then where did I go? I went this direction. So I went down to 0. I went down to 0 over some interval of time. And so this is our 0 mark right here. And then from here, I went 8 meters. So I can go from my 0 back up to about 8. We'll say right there. And this can be 8. And then I went from that 8, and I went 5 meters back down to 3. So I can go from here down to about 3. So that's what my position versus time graph would look like. And you more often see this sort of representation than the sort right here. And then total time, we said it took us 15 seconds. So the time down here, the total time from our start to our end is going to be 15 seconds, and this models our motion.